So in this, our final lecture, we're going to learn about three Nobel Prize winning ideas in quantum mechanics, relatively recent Nobel Prizes, not the original invention of the theory, but some more advanced applications in particle physics and also in many-body condensed matter physics. We've done a lot of hard work throughout this course to get us to the point where we can really understand the ideas behind these three different Nobel Prizes, not just at a sort of, oh, I saw it on the Science Channel level, but really, really understand it. And what brought us to the point of being able to understand these is the developments that we had in our last lecture where we learned about the Feynman sum-over histories. So let me remind and call to mind some of our key results from last time, and then we will see how from these results we will be able to understand these, again, Nobel Prize winning ideas. So the basic idea is that we were learning about this Feynman sum-over histories by applying it to a particular example, which was this inverted square well potential bump, like so, where we then had three different regions, really. Region 1, region 2, and again we go back to the same type of region, which has the same wave vector 1, and the potential then in here extended over a distance a. And we were involved in trying to calculate then the probabilities of reflection and transmission when we send a particle through the system. And we had learned that when we solve the time-independent Schrödinger equation, where we take a slightly different normalization on our plane waves, on our pure momentum states, we can arrange things conveniently then so that they fit with the first idea in the Feynman framework, which is namely that if I want the probability of an event, such as the probability of this reflection, it is given exactly by the square of this quantum amplitude r. And likewise, the probability of getting a transmission was just the modulo squared of this transmission amplitude that we are trying to calculate. Now, we also showed you how to introduce Feynman diagrams, where these little wiggly lines with a number in front of them actually mean something very precise mathematically. There's really a definition. This is a shorthand for writing the following equation, where if I have a line that's a wiggly line that's touching some vertical line which labels a location x with a number in front of it, what it really means is that number c times then a pure momentum state traveling in the corresponding direction, written down so that it's centered at the location that the little wave is touching. So that would be e to the I k x minus a. In this case, it's a plus sign because the wavy line is pointing to the right. Normalized, though, by the square root of the classical velocity, which was just the right normalization so that we kind of conveniently get this very simple Feynman idea for getting the probabilities as the squares of the corresponding amplitudes. The next thing that we did is we considered what happens if I send in a unit wave, like so, into this system, and then I work very hard to make sure I'm always satisfying my boundary conditions. And then we kind of went back and forth playing this whack-a-mole kind of a game to make sure we were always satisfying our boundary conditions. And fortunately, as we did this, eventually we got to a situation where there was no more wave ricocheting back and forth between the two barriers, and then we could simply total up the entire number of waves coming out on this side, which would give us the net reflection coefficient, whereas the total amplitude of these waves would then give me the transmission coefficient. We further learned then that in order to calculate each of these different contributions, which represents a different Feynman history, the amplitude of each one of these then just becomes the product of different fundamental events that are happening as the wave bounces back and forth. We learned, for example, that we needed the following fundamental events. The first event is when we're coming in here from the left and we hit this up step in the potential. That event we indicated as so, and this represents then where we solve a problem of just a step up in potential, right? We don't have to worry about what's happening later on in the system. The rest of the framework will take care of that for us. We just need to know the quantum amplitudes for when we hit a step up like this for transmission and reflection. So we would get this by solving the time-independent Schrödinger equation, which would tell us the corresponding transmission coefficient and reflection coefficient. And to help us keep track of things, because this is a situation where as I'm traveling along, the potential is suddenly going to step upwards, I'd label these as R plus and T plus because there's going to be a gain in the potential. The next thing that happened to our wave is that it had actually propagated back across the system. When it does so, it picks up a factor of p, as I've indicated for you here. And we also learned that another event that we have to track is that sometimes we're talking about the wave traveling back across the system. In either case, we get the same factor, which we called p. If I'm thinking about a transmission, the next type of an event I need to consider is when my wave is coming along in region 2 and then suddenly moves into region 1 and is transmitted out of the overall system. In that case, the potential would appear as so, where I'm going from a type 2 region into a type 1 region. Correspondingly, there would be a transmission and reflection coefficient. And now, because I'm going from a region of higher potential with a step down to lower potential, we decided to label these as T minus and R minus. It's clearly physically a different type of situation from this, where the potential here is moving upward. So we know we're going to need slightly different labels. There was one final interaction that became important, one final process, and that is sometimes when these waves are traveling back in this direction, when they hit the original boundary, they can either be transmitted or reflected again. So we need a set of amplitudes when I'm coming in from the left towards this upward step. That represents the situation in this diagram, but now I'm coming in from the side. So even though I'm still hitting what we were calling the up step, now I'm hitting it from the other side, and therefore we would expect we would get different coefficients. However, if you look at this diagram, it looks very much like the diagram over here, right? The only difference between these is that there's a little mapping where we can let x go to minus x and just flip our x-axis around, and these would become exactly the same thing. And because our physics can't depend on our choice of axis, you can then decide or realize then that this transmission and this reflection coefficient have to be the same as they are in the other case. The quick mnemonic for remembering this is I'm traveling in region 2 towards region 1. What I see when that happens to me is I'm going from a higher potential to a lower potential, so of course it should be some kind of minus reflection or transmission. The final type of an event, which actually didn't come up for us for this particular problem that we were solving, is what happens when a particle is coming in from the far right towards my bump up. Something like I'm indicating for you here. And you will notice I'm going from a lower potential to a higher potential. So this is a step up if I'm coming in from this side. So we would expect then that our coefficients then would be a T plus here and an R plus there. If you want to be able to prove that mathematically, again, you will notice that this is just the x goes to minus x version of, in fact, this particular situation. Finally, by simply solving then for these rather simple scattering type problems of an infinitely long constant and then a slightly different constant, we can recycle some of the results we had in an earlier lecture, and we determined the very specific values for R plus and minus and T plus and minus for these particular cases. And the last little bit to remind ourselves of is, well, we actually had derived last time what this propagation factor had to be, and it's simply sort of like a plane wave factor. It has e to the I, the corresponding k, which is a k2, because here I'm propagating between my bumps, right? I'm in region 2, times then the corresponding distance a. Very good. So that then laid out the fundamental events. And then we learned how to actually determine the total transmission coefficient as the sum of all of these contributions. Each individual contribution, as you can see, comes from a different number of times I've bounced back and forth between my two barriers. So to organize ourselves, we wrote these diagrams, which said, well, the simplest way I can simply get the first contribution to the transmission is where I had just transmitted across the first barrier, propagated across, and transmitted across the second barrier in order to produce this first piece of the final wave. That then looks like this particular history for getting from the left side to the right side, which has these corresponding factors. There's a T plus when I go up the up step, which is the first piece that I hit. Then there's the P for propagating across, and then finally the T minus because I'm now transmitting through this final down step. That's my first term. My second term then involved, if you look on this diagram, it was where I came across, the wave came part of the reflected wave then hits the original boundary, partly transmitted to make a contribution to the reflection, but also part is reflected again and finally transmitted out. That corresponds to this sequence of events, which has the t and the p as we had before to get across. Then there's this ricochet event where I reflect off this boundary and then I propagate across, that's this term, and then I reflect off the other boundary, that's this r minus, and finally propagate back across, and then of course I then have to transmit out. So that would give me this term. When we look at the next type of an event, it's the same idea, except now I have bounced back and forth one extra time. And at this point, we began to notice there was a pattern, a structure in this infinite series that allowed us to sum it very conveniently. You will notice that every single one of my terms begins with a t times a p. That is because they all begin where they have to go through the first barrier and propagate across. They all do that. So I put a little dots here to separate out those particular factors. Also, they all end with this final transmission factor to go out into the final external region. So what we notice then, the difference is just how many times we ricochet back and forth. In this case, there was one ricochet event. In this second case, I get two of those that have an RP, and then again, it would be an RP. So I just have this factor repeated twice, times then, of course, the t minus on the way out. So each of these little bubbles is another set of these factors. And then, of course, as we continue on, we're just generating this very nice geometric series. And we recall how to sum any infinite geometric series. It is always just the first term, which is this one, which I've copied down, divided by then 1 minus the geometric ratio. And this ratio in this case is just this repeated ricochet factor, r minus p, r minus p. And those then are the results that we had at the end of last time.